Hello everyone, I'm Zichi. Today I'm going to talk about Find Any Part in 3D, which is our ICCV 2025 highlight paper. We have all witnessed the power of AI in the digital world. Now we need to bring it to the physical world. And we believe the first step of that is semantic localization. Imagine this cute robot wants to find the drawer knob. The task is locating the exact points of the knob based on the language description. You can imagine this capability also has broad applications in AR/VR or design. This task is open-world part segmentation in 3D. I highlight open-world, part, and 3D in different colors because they represent three unique requirements of this task that make it challenging. Why? First of all, there's no large-scale data. Secondly, collecting human annotations for 3D is very difficult. In this work, we propose a solution, which is to build a data engine that can self-annotate any 3D object with any part using natural language and foundation models. And there is no human in the loop. So how do we build the data engine? We start from unlabeled online 3D assets from afterwards. Do multi-view rendering. Use grid point prompts to pass it to SAM to get 2D masks. And then query Gemini for the part names. Do geometric back projection to get the points, and use VLM to embed the labels. In this fashion, we annotated in total 2.1 million parts, 761 categories, which is over 1500x the unique parts in existing datasets combined. And below we show some qualitative examples of our data engine annotations. Now we have the data. It's actually non-trivial to train the model because first of all, some points can be unlabeled, and second of all, each point can be labeled with different texts from different viewing angles. So we devise a contrastive scheme. We train a model, Find3D, which is based on transformer architecture, PT3, and we predict one feature for every point of an object. Now we get data from the data engine, which comes in the form of set of points, feature pairs. So for the corresponding prediction, we pull the features of all the points inside that set. This gives us a positive pair. We can repeat this process to get multiple positive pairs, and now we are able to do a contrastive loss. So now we have a simple model, simple training recipe, and it can handle ambiguity of language. And finally, it's also really scalable. So how does our model do? Before I show the numbers, I want to show some qualitative examples first. These are for common objects with common text queries, as shown below. First, we see how the baseline does. They don't do well because they are trained on very small constrained datasets. In contrast, our model does a lot better. Here, I also show a lot of out-of-distribution generalization of our model, which includes cartoon characters that are far from the training distribution, as well as 3D reconstructions of in the wild iPhone photos. Now comes to quantitative results. First, if we evaluate zero-shot MIOU, we achieve 260% improvement, which is a great lead on baselines. And secondly, we compare on a dataset that the best baseline is trained on, whereas our model is evaluated zero-shot on this dataset. Even in this case, we see 176% improvement. Finally, in terms of inference time, we are 6 to 300x faster than existing models. We also show a scaling analysis, which corroborates the importance of our data engine and scale. Basically, if we look at the red point, that's the number of existing datasets combined in terms of training object categories. And now as we scaled up towards the green point, which is the number of categories we train on, we see a steady growth in zero-shot performance. Finally, we also contribute a new benchmark that covers a lot more diverse objects. Finally, for takeaways, I want to emphasize that we do believe in the learning of bitter lesson, which says that data scale-up is very important for generalization, but we also want to acknowledge that internet data is hitting a ceiling for important but hard tasks like 3D open-world part segmentation. So what is the solution? In our task, we show that if we can build an automatic data engine, then we can scale up towards true generalization. Thank you.